presentation. It's good to be back in Warsaw. So, as Wojtek said, I want to tell you something about extremal horizons of this knot type, which I will argue that is connected to non-trivial topology. So, this is a work that we have recently put on archive, and it has been in preparation for quite some time. The original idea for this construction was already given by Professor Lewandowski, so it was something that we have already started back when I was a PhD student here. And what we have put on archive recently is somehow the best way we could finish this idea. We meaning together with Eric Book and Denis Plebański-Demiański and some notes that Professor left us. Okay, so let me start by telling you about. So there's a natural motivation for study of such horizons, and essentially it comes in two parts. So first of all, why study horizons of non-trivial topology? So I will tell you something about Plebański-Demiański. Plebański-Demiański spacetimes, where horizons of such type occur naturally if they are extremal. Also, I will tell you something why we care about extremal horizons. I will go through the new construction. First through the basic definition of isolated horizon structure, and also about what is new about this construction, why some hints why it hasn't been done before. In the end, I will tell you how the solutions that we found for such horizons work, and what are the relations to other known solutions. Because, well, it's an area with quite a literature, I would say. Okay, so first of all, what are the Plebański-Demiański spacetimes? So the proper definition is probably that they are the most general solutions of Petrov type D. By Petrov type D, I mean that the value tensor has two principal null directions. This is a classification for an eigenvalue of the value tensor of the spacetime. And there are most general solutions to the Einstein equations in 4 dimensions with cosmological constant and electromagnetic charges, such that this electromagnetic field is aligned with the principal directions, of which there are two. So some physical reason why do we care about this family of spacetimes is such that they are closely related to something that we most commonly study astrophysically, which are the Schwarzschild and Kerr solutions. So this type of spacetime can be thought as an extension of both Schwarzschild and Kerr. So in general, there are 7 real parameters appearing in those metrics. In some cases, they have their traditional interpretations. In some other cases, there are just parameters which are subject to further interpretation. So we have some mass, which we can see that this is the Schwarzschild mass. There is some Kerr rotation parameter. There are electromagnetic charges. There's a cosmological constant. As usual, the charges enter through the Maxwell part of the Einstein-Maxwell equation. Cosmological constant is also present in the Einstein equations. The acceleration is one of the mysterious parameters in this family. So the usual wisdom is that if you consider accelerating Schwarzschild, then in the weak field limit, this solution looks like a pair of linear circles. So that's why we say that it's accelerating. However, there were some recent papers by Podolsky and Novia that connected this acceleration to the type of spacetime to the radiation being present at the null infinity. So maybe there are some different ways to think about it. Finally, there is the knot parameter. So there's a whole problem of interpreting this guy, which I will not tackle fully today. But for us, this parameter, it introduces singularity at the axis of the rotation. in one approach, and the other approach introduces the need for this non-triviality of the bundle, which I will tell you something more in a second. So those solutions, I think, are almost 50 years old right now. However, there's still lots of research going on in the neighborhood of those solutions. There's still a lot of inspiration coming from them. So some recent results, which were quite famous in the exact solution segment of general relativities, that they have been found. Podolsky and Nestorino found the explicit form of accelerated tau-NAT ADS. So just the combination of just having mass, acceleration, and NAT parameter, which was previously thought to be impossible in this configuration. And some other recent famous paper was that Podolsky and Ovcharenko found, Nestorino probably also, found the curve in constant magnetic field, embedded in a constant magnetic field. So there's still a lot of inspiration coming from this.
Można pytanie?
Jasne.
Cześć, Piotrek Szluściel. Bo ja patrzyłem na tą pracę Podolskiego i ostatnio nie udało mi się zrozumieć, czy te ich rozwiązania są osobliwe, czy one są regularne, to jakoś tak było podejrzane.
Rozwiązania z przyspieszonym tobem na ten?
No ta nowa praca Podolskiego, tam?
Znaczy, bo to są dwie nowe prace Podolskiego, oba te
no dobrze,
są...
Znaczy, krótko mówiąc, czy są tutaj te jakieś takie metryki, które nie mają osobliwości w tych przyspieszonych? Czy one mają osobliwości gdzieś na zewnątrz horyzontu?
Okej, znaczy to są oczywiście dwie szkoły interpretacji. Jedna jest interpretacja Bonara, w której tam jest osobliwość tożkowa, znaczy jest Misner string na... sorry, I should switch to English. There's a Misner string at the axis. And
so there is a string in these solutions.
Yes, yeah. I think they suffer from the same type of pathology that tau-NAT spacetime suffer from. It's the same situation at the axis. So there are closed time-like curves, naked appearing outside the horizon, and there is some problem with conical singularity. Yes.
But tau-NAT does not have any singularities. I mean, it has closed time-like curves beyond the horizon, but outside well, the generators are closed, but there are no singularities outside of the horizon. And so, when in this larger family, does it have singularities or not?
I think that tau-NAT has singularities outside the horizon. I will just have a slide right after this.
Okay.
So, maybe this will clear out. Please ask me if it's not clear. Ask me later on this.
Okay. Okay. Thanks.
Yeah. Thank you. So yeah, the simplest member of the tau-NAT family, of the Plebański-Demiański family with non-zero NAT parameter is the so-called tau-NAT spacetime. So in the Schwarzschild-like coordinates, we can see that it's very closely related to Schwarzschild. So this should be our score. Meaning that for L equal to 0, we exactly recover Schwarzschild. However, for L not equal to 0, there are some new types of phenomena appearing in this spacetime. So first is that at R equal to 0, there's no longer curvature singularity. So this is somehow regularized by this additional term here. And the second is appearing of this dual cosine theta minus 1 d phi part. So if you look at this one form omega, which I call omega is just dt minus this guy here d phi, a is just 12 cosine minus 1. So you can see that this one form is not continuous at theta equal to pi. So this is usually taken to mean that there is some kind of singularity at the half axis and the theta equal to pi half axis. And in fact, one can show that this is a quasi-regular in the classification of singularities, it's a flat irregular singularity. And the other axis is fine, right? Because at the other axis, this cosine theta minus 1 would be just 0, and this singular part would vanish. So, of course, what was very shortly noticed is that this behavior will be changed with some coordinate transformation. So if you introduce some change of coordinates, so t minus new time coordinate, which is t minus 4L5, so this is somehow twisted or rotating coordinate. You change the behavior such that there is a plus here. There is not minus, like here there's a plus. So this should be for curve, well, curve parameter equal to 0, so it shouldn't be here. And now the behavior of the singular axis switches. So in the first part, in the first coordinates, we had singularity at this blue picture at the theta equal to 0, and the second part, the second coordinate singularity is the red pictures, singularity is at the other pole. And the Misner interpretation is based on his idea to get rid of this of both of the singularities by taking a non-singular part of one solution, non-singular part of second of the solution in the other coordinates and gluing them together. So they're just two copies of tau nav, one with singularity at one pole, the other is singularity at other pole, and just gluing them together. So his solution is now non-singular in the sense that well, we have two non-singular copies, right? There's the price that we have paid is that in the process of this, the t coordinate has become cyclic. I mean periodic, so maybe better that the d over dt has become cyclic. So this means that not only close to the axis, but in entire spacetime, if the d over dt is a time-like vector field, then there are closed time-like curves. So the topology of the spacetime changes to S3 times R, or equivalently to a U1 principal bundle over S2 times R. And those parts could be actually easily seen in this form of the matrix. So the T, theta and phi, they play the role of the coordinates on S3. And the R part is on the R. So this would mean that the spacetime looks like it's foliated by a family of three-dimensional spheres, each of some radius. And in this family of spheres, of course, must be all of the horizons, meaning that if there are horizons present in this spacetime, and there are, they also need to have a topology of S3. So this is quite unusual for the horizons. Yeah, and this is the part that we want to construct. Okay, so this very simple observation can be extended to the entire Plebański-Demiański solutions. So in the Plebański-Demiański matrix, if you assume that you have expanded now geodesic congruence and that there is a distinguished family of two-dimensional surfaces with spherical topology, then you obtain something that looks like a black hole solution, and this black hole solution is often called either like a general Plebański-Demiański black hole or just the accelerated Kerr-Nat ADS spacetime, just by combining the names of the parameters appearing in this metric. And this doesn't look very nice, but if you look close, long enough and close enough, you can see that this is similar to Kerr metric in the Boyer with coordinates, just with some additional functions. And importantly, there still appears this type of singularity where this one form is not defined as one of the poles, right? Because we have the same story. So So this function A vanishes at one pole, it doesn't vanish at the other pole, and the entire one form is not continuous there. And this behavior, of course, can be changed with different coordinates choices. And something that we have done with Professor Lewandowski was to extend the standard Misner interpretation to the generic Plebański-Demiański black hole spacetimes. However, this requires some mathematical machinery, which I don't want to go into. Maybe the one point that is worth emphasizing is that for the tau knot, the cyclic Klinik vector field was just d over t in the standard Schwarzschild coordinates. Now one has to take the cyclic Klinik vector field is just some generic combination of d over dt and d over d5. So two Klinik vector fields which appear in this spacetime, and it generally depends on the parameters, and there are up to 4 Klinik horizons in this spacetime. They are given by the radii are given by the zeros of this Q, which is 4-degree polynomial, and in fact, some of them could be extremal. So we wanted to, yes?
No, I think it's worth to emphasize that Q and P are fourth order polynomials.
Yes. So in the original form of the metric, this is of course true that P and Q are both fourth order polynomials. Here, this form is slightly simplified because P is factored, like quadratic polynomial, which becomes sine theta squared, is factored already from the P. So here P is the second order polynomial, it's quadratic. But in the original coordinates, this is of course true. Thank you. Yes.
Can I ask about this degenerations? I mean, there is a family which is this, it's called ultra cold parenthesis, where 3 of these horizons. So you can have a triple zero and a simple zero, and so 3 of the horizons coincide. Ultra extreme limit is in this setup. Can all the 4 horizons coincide?
I think if there is, I think the answer is yes. You need, but you need this polynomial to be generic, to have all terms, and this happens if the acceleration parameter is non-zero.
Yeah. But you would think that the situation I'm referring to will be highly non-generic. I mean, you have a quadruple root.
Yeah, okay. It's non-generic in the parameters, in the sense that all parameters are present, and there are probably some strict constraints on them, as you say.
Okay.
I think that I haven't looked exactly in this case, but I suspect this is what happens. Thank you. Yeah. So if there exists extremal horizons, we want to investigate their structure here. So maybe some slightly pedagogical slide. What are the extremal horizons? So first of all, there's a proper definition of a black hole horizon. It's just a region of the space-time that, roughly speaking, from which the information cannot escape to the infinity. So we look at the future infinity, and we look at all of the points that can be reached from the future infinity by a past-pointing causal curves. And if there is some region in space-time that cannot be reached by such curves, then this is a black hole region, right? This is a proper definition of mathematical no escape intuition. And of course, the black hole event horizon is the boundary of this region, this region is 4-dimensional, the boundary is 3-dimensional, this is the right dimensional for the horizon that we like to have. So this is quite unwieldy definition. And actually, Hawking showed that in stationary spacetimes, if the Einstein equations are satisfied, then black hole horizon should be Klinik horizon. So this somehow shifted the interest of the horizon study to study Klinik horizon. I mean, not only, but this is one of the big topics. So the Klinik horizon assume that there exists some vector field, which is an isometry of the spacetime, meaning that this vector field lead drags the spacetime metric. So such thing is called Killing vector field, and the Killing horizon is just by definition some hypersurface where the norm of this vector vanishes. However, the vector itself doesn't vanish. So, right? So this is this means that there's a field which is null and non-zero, and must be of course tangent to the horizon. So the usual case, usually one shows that this Killing horizon for spherical spacetimes has the topology of S2 times R. So this is like a S2 cylinder, right? And there are some nice properties which one can show, that there are some causal properties which, because the surface is null, so there's some causal separation. It's an expanding, meaning that roughly this S2 part is time independent. And some important quantity which is associated with the horizon is so-called surface gravity. So this is if you look at this, then you just see that this is just self-acceleration of the Killing field that generates the horizon. And the proportionality constant, I mean, this proportionality term is just surface gravity, what we call surface gravity, and the so-called zero flow of black hole thermodynamics gives us the fact that it's constant on the horizon. And so the extremal horizons are such that the surface gravity vanishes. And maybe some points of interest is that if you look at the Hawking, the temperature, the Hawking rotation, it's proportional to the surface gravity, right? So the zero temperature limit is somehow the non-repeating horizons, and sorry, yeah. And why people care about this is because the quantum effects associated with this Hawking radiations are most prominent in the near horizon case, which points us to really study the extremal horizon as sort of a zero approximation of the near horizon solutions, which there's a lot of interest. Okay, so this previous definition. I forgot something. It's good. Okay. Going back to the horizons, this definition, even for Killing horizons, is already has some maybe hidden requirement, namely, or maybe not so hidden, that there exists this Killing vector field. And this Killing vector field is a spacetime Killing vector field, meaning that it has to exist in the entire spacetime. So this definition is somehow global. While we would like to have some local notion of the event horizon. Because, for example, we would like to do some numerical calculations, and we would like to, at some point in our calculation, see that there is a horizon without needing to extend the calculation to the infinite time. So here comes the structure of the isolated horizon. So as I said, this is an attempt to define something that captures most of the properties of the Killing horizon. However, it's local in the sense that we only would require that the Killing horizon exists at the horizon, and possibly in the neighborhood of the horizon, the spacetime could be dynamic. So this is usually done in two steps. So first one defines the non-expanding horizons. So this is a three-dimensional null surface H, which is equipped with a degenerate signature. It's degenerate because degenerate metric, because signature has 1, 0, right? And we here assume that there is also this H has topology of some bundle over two-dimensional compact Riemannian surface. So this typical example for Kerr and Schwarzschild that I have showed you is example just for a trivial bundle where the topology is just a product. So yeah, exactly. I have this here. So we want to a slight generalization of the standard definition. And on this two-dimensional surface, compact two-dimensional surface, there is actually a Riemannian positive definite metric which corresponds to those two pluses in the signature of the metric, which I will in this talk just everywhere call G. This surface is non-expanding, meaning that if we have some Killing vector field pointing in the null direction, in the direction of 0, so some field pointing in this direction, then it must be Killing field. And of course, this is not given. This is given only just up to some function. So some scaling are possible. And the important part also is that H is null. So if it's null, then the metric given on H does not uniquely constrain the connection on the horizon. This connection might in fact not even exist. So we are forced to equip this definition with some externally given connection, and we require that this connection is metric for the Riemannian part. So that we only analyze the Riemannian part of the metric. Of course, if the horizon is embedded, then we already are provided with such natural choice of this connection, namely the restriction of the space-time connection to the horizon. Then it can be done. And the isolated horizon is, of course, the non-expanding horizon, which is for which we also require that this connection commutes with taking a linear derivative along this null field. This has some nice conclusions from this, namely that only rescaling of this horizon generating field by some constant are admissible. And now we can also define this what I call rotational form omega. And you can think about this omega as encoding this part of the connection that is not restricted by the metricity of the horizon connection, and it's also something that is conserved by transport. Again, we have all of the ingredients to find surface gravities. Again, the self-acceleration taken at the horizon, and right now we don't have any field equations, so we just assume that it's constant at the zero for holds. And the last ingredient is the capital omega, the so-called pseudo-scalar invariant. And well, probably the easiest intuition is that if capital omega vanishes, then the horizon is not non-rotating. This is what we'll assume. And again, because the rescaling of this field L are only given by a real constant, this means that surface gravity is again given only up to some real constant. This means that it's natural to talk about the zero case, where the extremal case and non-extremal cases. Right, one of them feels there is rescaling, one of them does not. Okay. So far I have just assumed that there is just some bundle structure on this surface on the horizon. What one can further assume, or introduce, is the principal bundle structure, meaning that there is some group acting on the horizon, and there are some more technical requirements. And this group G acts via flow of some Killing symmetry of some Killing vector field, which this field is. I would say that this field generates the group, and this occurs if you want the group to be connected then and generated by one Killing vector field, then there isn't much choice. It's either real line or E1, which is just a circle. So it leaves us the possibility of classifying all such horizons by either the base space of the bundle S and of the group. So I will focus mostly on the case where this group is a circle. So this is the so-called Hopf bundle. More complicated bundles, E1 bundles, are also easily possible. It's easy to construct them also. So now the question is, can we somehow introduce this E1 structure in some natural ways? So in a natural way, by natural way, I mean, can we, for example, introduce the U1 connection, so the choice of horizontal vector fields in this horizon, using some objects which I have already defined in those slides. So what objects have we have been given? So first of all, the metric tensor could be the volume form, could be the rotation form, could be the rotation scalar, could be connection. And what it turns out that there of course exists a natural choice if we started from a natural point. So by natural point, I mean that if this group was already generated by the field L generating the horizon, then the connection could be defined as just rotation form divided by kappa, and as the connection in one form has to take values in Lie algebra, we also multiply it by the Lie algebra vector associated with the Killing vector field L. And it satisfies all of the requirements for the connection and gives us some natural bundle curvature. However, as you can see, this approach breaks explicitly for kappa equal to 0. So this is what we have studied previously for the non-extremal cases. We need another approach, right? And we probably cannot use omega, as there are one can, for example, show that on N is two surface transversal to scaling vector field L, the omega is the same, right? You cannot define any non-trivial bundle using just omega. So we did it in a sort of unnatural way. we constructed in coordinates of the horizon. So what is the rough prescription? We take two three-dimensional manifolds. In the cases of our interest, these are those, namely to construct a Hopf bundle, we take those three-dimensional manifolds such that one is the two-sphere without one pole. So, for example, P plus is the pole theta equal to 5, and P minus is the pole theta equal to 0. So this is a sphere without a point, right? Without one point, and we multiply this by S1. So we have two manifolds with such topologies, and we introduce on those manifolds, we introduce we equate them, just simply said, with the metric tensor rotation one force first in coordinates theta phi d, where theta goes from 0 to pi, unincluded because we have excluded this point. Phi is just angular cyclic coordinate, and v, again, v, because we want to construct a U1 bundle, so this v will be the cyclic, the periodic coordinates, and also lives on a circle. And we could write the expressions for the metric and for the rotation one form in those coordinates. And the same can be done for the other dimensional manifold, just with some coordinates with primes. And there are some different. So, for example, here there's beta minus, here's beta plus with different orientation, and we maybe some way to think about this is that if you disregard this d over this dv part in the matrix, then those this looks like a metric, like a spherical metric, however with conical singularity. Because if beta minus would be not equal to 1, and d over d phi is already chosen to be 2 pi periodic, then this is a metric with conical singularity. We do this the same on the other manifold, and then we introduce the transformation law. And this transformation law, the most important part is what happens for the big coordinate. This is essentially the same way that a couple of slides ago I told you that you could switch the singular behavior of the two axes, and this is exactly the same type of transformation, which leads to the U1 bundle structure in the spacetime. And well, when it leads to this two three-dimensional manifolds gluing together into something that has a topology of a Hopf bundle, U1 bundle over two-dimensional sphere. Okay, so now, as I said, d over dv is cyclic, so it generates some U1 action. There's some other Killing vector fields which have a right combination of d over dv, which is cyclic, and d over d phi, which is also cyclic. This also gives us a well-defined U1 action. And yeah, and generally, neither of them is null. So because the null field is L-line, and you can see that that psi L becomes null. However, this only happens if the betas, so the conicities of those two manifolds, are the same. Then L just reduces to L with some scaling. And of course, this is maybe not exactly apparent from those metrics, but we have some null field, and these metrics are determinant Horizon metric. You could easily generalize this construction not only to achieve Hopf bundle, but to achieve some U1 bundles over S2 with higher term number. We just essentially change transformation law in some slight way. Okay, so let's go to the final part. We assume that that this horizon has a principal bundle structure, and this is quite important assumption for us. So because it allows us to reduce this entire problem to just looking what happens on the spaces of on this two-dimensional Riemannian part, on the base space of the bundle or of the space of the null generators, or in this case, all names for the same object. So from the three-dimensional metric, from just G3 given on the bundle, from the omega 3, also given on the three-dimensional horizon, we assume that there are some that you could project them to something that lives only on the two-dimensional part. So this is a nice reduction of the problem. And what it turns out that what you get generically is the metric on the base of the null generators, which is a metric on S2 with conical singularities. Generically, if the betas are not equal to 1, right? Essentially, this is what will happen if you project out to if you project down to S2, then this d over dv part, you can neglect this, and you will get a metric tensor on a sphere with conical singularity. However, as it turns out, the omega is regular long-term on S2, and this is not exactly clear from this definition, but what happens is that you can show that for kappa equal to 0, it always scale the angular coordinates such that the omega is regular at both coordinates. So now our goal, I presented you the construction, is to find all of the intrinsic horizon geometries given by G and omega, which are admissible by this construction, and are subject to Einstein equations with cosmological constants.
Can I ask?
Yes.
So you can relax the curve type case because you're allowing conical singularities on the spatial cross section.
Yes.
But then you say that omega is regular on S2.
Yes.
So what actually happens with omega at these conical singularities? What sort of behavior near the singularity do you?
I think it vanishes close to the single.
Does it follow from you imposed it, or it follows from?
It follows from this form of the basically it follows from this form of omegas, and if you impose that this omega is regular at one of the pole, for example, it's regular at the pole that is covered by those coordinates, then if you then this already gives you the fact that omega projected down to S2, of course, will be regular in the other pole, like even from this other line. Yeah.
I mean, if the metric on the sphere is regular, then you can show that omega, before you know that it's kerr, you can show that omega vanishes at 2 points.
Mm-hmm.
So if you have a conical singularity, is it that one of these points has to be at the conical singularity, or is there an additional zero of omega?
No, the omega vanishes as you approach the conical singularities. It's also exactly those 2 points, I think.
But you can have only one conical singularity. The sphere.
But there is this symmetry, this axial symmetry. There is axial symmetry already.
So how many zeros will omega have?
So then they need to be 2 zeros because an axially symmetric one pole will vanish at the pole. Yes? That just follows from axial symmetry.
But is there an assumption already that this sphere, that there is an axial symmetry, or you will work about?
I think there is
Yes.
assumption. Yes.
Yes. So if this hasn't been entirely clear.
You assume that there is also an additional killing factor on this S2.
Yes. Sorry, I
Okay.
have to emphasize this more. It's actually a symmetric case.
Okay, thank you.
Yes. Thank you for clearing this. Yeah. So what we do is we of course try to find equations constraining this, and of course this equation has been already studied very much in the literature. So if you impose Einstein vacuum lambda vacuum Einstein equations on your spacetime, then this gives you some constraint of the geometry on the horizon. So from 4-dimensional, you have a reduction to 3-dimensional situation. And what is quite remarkable for the extremal horizons is that actually there's even a further reduction. So the Einstein equations reduce to equation which has many names. I think we call it the extremal horizon Einstein equation, but it's also under the name of the horizon geometry equation or quasi-Einstein equation. It appears in various places in the literature. However, this equation only uses objects defined on 2-dimensional surface S, which is quite remarkable because well, we have imposed this Einstein equations on 3-dimensional horizon, and if it's extremal, then it further reduces to 2-dimensional situation. And here RLB is of course the rich tensor associated with on S. And there is of course this equation has been studied very extensively in the literature. So if you assume some axial symmetry, possibly conical singularities. Then, of course, there's a very famous classification by Lucetti and Kunduri, who derived all of the solutions with axial symmetry to those equations. However, they're quite general. However, they suffer from maybe one drawback, is that they are slightly unwieldy. By which I mean that it's not easy to see where exactly are the faults in their solutions. So somehow this forces people to every couple of years reinvent their solutions in some form that is suitable for someone else's needs. So one can show that if S would not be a two-dimensional sphere, with some higher genus Riemann surface, then only static solutions exist, and such that the G is a constant curvature and the omega vanishes, and there are so-called, in a sense, there are trivial solutions. One can ask what happens if there are no conical singularities, and you don't assume axial symmetry. Are there any solutions? And again, this is a no-go. So a very famous result, quite recent also, is that so-called rigidity theorem holds for this for solutions to this equation, meaning that if S is smooth, then axial symmetry always has to exist. So essentially, this gives us the fact that already the classification of axially symmetric solutions were the full classification for the smooth case without conical singularities. And to be honest, this is the most relevant part of the solutions. So we have also tried to solve this equation in some manner that suited what we wanted to do. That would explicitly give us G and omega in a form that would be useful to this construction. And we did some standard tricks that one can do in this case. So again, because we have assumed the axial symmetry, but possibly there's a conical singularity, then the phi coordinate is not necessarily 2π periodic, but the overall metric is the standard metric for the axially symmetric solution on a or just axially symmetric solution. And if you assume that P has two zeros, then this is a sphere, right? And this is for G. For the omega, there exists a standard decomposition into the exact and coexact parts, which could be written in those coordinates where B and U are some, let's say, potential functions to be determined. And if you plug those forms into this equation, you get something that is actually manageable. So it turns out that there's natural splitting in this equation. So there's a trace part. So if you trace this equation, then you get something that essentially involves only omega. So to solve this for the omega, you still need to determine this function P. However, this function P is constrained by the trace-free part of this equation. And it's a second-order ordinary differential equation. In this case, so it's entirely manageable. It's possible to derive the generic solution. And you solve for G, or for the function P. You solve for those functions, plug in P, and you arrive at the generic solutions. And
so you're making an additional assumption here, right? But this omega inherits the symmetry.
Yes, this is this. It's not only the G it's not only the section that is spherically symmetric, is the entire horizon that is axially symmetric. Sorry. Yes.
No, I mean the one from omega. You can have a metric which has this killing vector.
Mm-hmm.
But a priori, you would think that there could be an omega which is not really derived along this vector.
Yeah.
But in the ansatz you seem to be making, does have
yeah, we assume this in the isolated horizon structure. That omega is sorry. No, sorry. Yeah. We assume that this is derived by the axial fit. Sure. Okay. So the solutions come into two main, let's say, classes. First of the class is the non-rotating, when the omega vanishes. So we can show that necessarily lambda is greater than 0, and the other case is the rotating, such that the omega is not equal to 0, and then any sign of the cosmological constant can be realized. I'm not maybe showing you the exact solutions. They're in the preprint, and I can assure that there are some nice pictures constraining the parameters. However, the equations itself are quite long in the solutions. So let me tell you about the relations of those two classes of non-rotating and rotating solutions to what we wanted to achieve. So we wanted to achieve something that actually embeds into the Plebański-Demiański spacetime with this Misner interpretation. And I think that this is what we have done. So first, one can say that any extremal horizon in the accelerated kernel ADS, if it's non-rotating, is of this generally is of this non-rotating type of the solutions to this equation. This is what I want to say. And then the non-rotating cases, they embed us a couple of funny possibilities. So first of all, because R0 is regular if the null parameter is present, it's no longer a curvature singularity, then you could in principle find such parameters such that the horizon is present at R equal to 0, and those horizons are non-rotating. If this horizon is extremal, then it's non-rotating. If the conical singularity of the metric G vanishes, then they embed as tau solutions. And also something that we wanted to tackle, but it was technically difficult, is that so the intuition is that the rotation should be associated with the curve parameter, right? This fact that the omega vanishes or not should somehow be connected to the curve parameter. So in Plebański-Demiański, if you set curve parameter to 0, in full generality, you obtain something that is accelerated tau naught with cosmological constant and possibly charges. And those solutions have been explicitly found recently in papers by Podolsky, Ovcharенko, and Storinov. However, they are somehow, unfortunately, in form which is so convoluted and depends on implicit functions of parameters that it's very difficult to say what are actually the geometries of the horizons contained in those solutions. So I would suspect that our solutions embed in accelerated tau naught ideas, but we haven't been able to confirm this directly. So what are the relation of our solutions to other solutions of this equation? So of course, and not only of this equation. There are two papers by Matejew and Podolsky who studied its extremal horizons in 4D. And they actually have found a full classification of the metrics of the horizon geometries with conical singularity. Maybe they use slightly different parameterization than we did. For them, the important value was the angle deficit, so they wanted to take the non-conically singular limit easily. And so our solutions agree exactly, our solutions for G exactly agree with their solutions. However, even their equations that they propose, they are equivalent to this extremal horizon Einstein equations. So there could be solved for omega, but they didn't do it. So, well, this is something new about our solutions, that we provide an explicit form of the omegas in those cases. There's, of course, famous, which I already mentioned, classification by Lucetti and Conduri. However, in principle, we could have used them, but if not for the fact that they don't, it's not clear, it's not easy to see where are the axes in their solutions. Because they actually solve these equations without assuming any topology. So it could be anything as long as it is axially symmetric. It could be plane, which is rotating, or something like this. So our solutions agree with their solutions if we assume that their solution have two poles. So if it's actually given on a sphere. Previously, there was paper by Professor Lewandowski and Eric, who, by some very similar procedure, obtained the solutions without conical singularities on a regular smooth two sphere. So, of course, our solutions have smooth and good limit to this case. Finally, there's another equation, which is quite, in a sense, it is similar to this equation, this extremal Einstein Horizon equation. This is so-called type D equation. So this equation constrains the geometry of the horizon such that, which is of type D, meaning that the Weil tensor at this horizon would be of type D. So again, this is an equation that lives on, uses only objects which are given on two-dimensional section of the horizon. So this is what we have solved. In a previous paper with Eric and Professor, what was actually also an inspiration for this continuation of the research, and we have found that all of the solutions to type the equation which give rise to the extrema, which are also to say. Yeah, we have found the relation between those solutions, because here the problem is that, of course, all of the solutions to this equation, this extremal Einstein equation, have to be solutions to the Petrov type D equations. However, we no longer, we don't know what is their Petrov type. So we have explicitly shown which of them are of Petrov type D. And something that neither of these previous approaches done was that we have put a constraints on the for those two classes of solutions. They are given by, of course, some parameters in parameterizing the solutions, and we have put constraints on that, which haven't been also done in any other approaches. Okay, so I have been talking for an hour, so maybe if you have some questions from
Questions?
Yes, so I didn't catch from the last part. So
Yes.
you find when this type D equation holds. Maybe I didn't understand it.
So any solution of the extremal horizon equation has to solve type D equation. However, the horizon might not be type D.
Ah, okay.
So what does it mean that horizon type D?
It means that if we embed this, then the Weil tensor would be type D at the horizon.
Independently how you embed, because maybe many no.
Yeah, definitely.
So that question. It's not that special.